From section 10.3 onward, we've learned a wide variety of ways to determine whether an infinite series converges or diverges. And in some cases, we've discovered that it's possible to determine the exact value of a convergent series, namely the geometric and telescoping ones. Those were the ones we were able to figure out specific values for sure. In this section, we're just going to step back and focus on the general strategies for classifying infinite series and deciding which tests are appropriate for a specific series, right? So on a test or on a quiz, it's not going to say, use the root test, use the this test. So you're going to have to determine which test to use on your own. And these are guidelines to try to help you make those decisions. Now, first and foremost, and I cannot tell you how many times students forget this, always, always look the series over and kind of see, do you think that sequence term, a sub n, will go to 0 as n goes to infinity? If it doesn't look like it's going to, then try the divergence test. It's not something you want to check all the time, but you want to kind of give it a quick glance and see if it looks like this is going to happen, but do it with a quick glance. Just kind of look it over. Then try the divergence test. Now, if it's a p-series, that's another thing, or a geometric series, we know exactly what those look like. So we know what p-series and geometric series look like. We might need to do some algebraic manipulation to get geometric series to be in the correct form. But otherwise, we generally know what it looks like. So just a reminder, geometric series, you may have to do a little bit of manipulation, like here we brought the 3 out and that turned it into the form that we were used to, that kind of thing. So you may need to do algebraic manipulation, but in general, we know what p-series and geometric series look like. We know what geometric series actually sum to. What if it's just really close to a geometric or a p-series? I mean, we know the p-series and the geometric series so well. What if it's just really close to it, very similar to those? Then try the comparison test. The comparison test is not something we do a lot of, but if it's super obvious, if it's just really similar and really close, then we would do that. For example, in this section, we had this series that was so close to the p-series. If I just knock off that +1, I've got it. That's the time when you use the comparison test, if it's just really obvious and easy to use. If it's a rational expression involving only polynomials or polynomials under radicals, you could try the comparison test and or the limit comparison test. Remember that to use the comparison test and the limit comparison test, everything has to be positive. You can't use it with a mixed signs. So let me make a note. All signs need to, or all terms need to be positive. No mixed signs. Right? Mixed signs would have to go to the alternating series test, which is down here, right? So alternating series test or some other type of test, right? Or perhaps the ratio test or the root test. Those could all do with mixed signs or negative values. Now, does it contain factorials? Factorials are a red flag that you need to use the ratio test. Factorials are almost always with the ratio test. Remember, factorial is like k factorial, right? That kind of thing. So if you see k factorial, if you see any exclamation point anywhere in the problem, you're going to probably 99% of the time use the ratio test. And then constants raised to powers. So if it involves things like 10 to the n or, -5 to the k, things like that. Because what happens with the ratio test is a lot of times they cancel out, right? So if you see a lot of powers or constants raised to powers or a lot of factorials, the ratio test is a good one. The ratio test, honestly, is one we use a lot in Chapter 11. Right. So, like I said, 99% of the time, factorials mean ratio tests. Matter of fact, always. So for our purposes, we will use the ratio test. If it's something to the n power, right? Or if it's n to the n power, something like, or, let me think, k, 2k to the k+1 power, something like that, then you would use the root test. If it involves alternating series, you can try the alternating series test if you're not looking for absolute convergence. The alternating series test does not show absolute convergence. So this is if trying to show conditional convergence. Use this one. Well, actually, usually try to show absolute convergence first, and if absolute convergence fails, then you go to the alternating series test to show conditional convergence. And your last resort, the thing you really want to avoid, if at all possible, is the integral test, just because it involves the most calculus, the most work. It can be really tricky, but it's your last choice, which is to take the integral and do all the hard integration work to show that the integral exists and therefore the function exists, or therefore the series converges. Right? If that integral converges, then the series converges. If the integral diverges, then then the series diverges. And it's not all written up, so this is more just kind of a guidelines to help you logic your way through a problem, right? So how are you going to choose which one? Now, what is given to you is this giant table as well, but it's not going to give you the logic behind it. It's just a reminder of what geometric series look like and what they are equal to if your absolute value of r is less than 1, what the divergence test is, what the p series are. Now you'll notice, by the way, and this can get people a little confused, p series and geometric series work a little bit differently from each other. I'll actually talk about those conditions for convergence in just a second. You have your comparison test, which generally I only use comparison test if it's just super obvious what the comparison is. Similarly, limit comparison, but limit comparison is more powerful and a little bit more elegant than the comparison test. So you don't have to have quite as big an idea of what's going on as you do with comparison. Of course, the alternating series test can prove conditional convergence. The absolute convergence, what the definition of that is, right? And then ratio root test and the integral test. It's all written here for you. So your conditions for convergence, your conditions for divergence, if they exist, and any comments. Students often get the p-series and the geometric series confused, so let me just make one more comment, which is that the geometric series, if I look at the number line, I'm just going to draw a little number line here. It converges if the ratio, absolute value of the ratio, is less than 1. So it converges in, I'm going to do convergence in pink. It converges from -1 to 1 if your ratio is in there. And it diverges if the absolute value of your ratio is greater than or equal to 1. So from 1 onward and from -1 onward. So this is diverging. I apologize if you're colorblind. So diverging is from 1 and beyond, and from -1 and beyond, right? That direction. It's an arrow. And then it converges in the middle. I can't write this word. It's too small. So it converges in the middle. It diverges on the edges. And 1 and -1 count for divergence. Now the p-series is not the same thing. The p-series is a power in a denominator, right? It's not a power series technically. I know I've used that term, but I was just kind of playing fast and loose with the terms. Power series is a whole other thing that we'll learn about in chapter 11. So here's 1 right here. So the p-series diverges when the power in that denominator, p, is less than or equal to 1. So from here onward. And of course, p can be negative. That is possible, right? And then it converges when p is greater than 1. Right? That's the difference between those two. So they all involve 1 and less than 1 and bigger than 1, so it can get confusing for students. So maybe that little that little number line diagram will help.